In the last section, we studied the bisection method and we saw some drawback in bisection method. For example, the slow convergence to the root. But the solution for the slow convergence is a new technique, a new method. In fact, we call it fixed point iteration. Before we start to fixed point iteration algorithm, we have to have a look at what is a fixed point. Let me show you the fixed point by an example. We have a function like this. Let me draw better thing like this. Okay. Now, if we draw a line y equal to x, and we know this is f of x equal to y. Now, if we draw line y equal to x and we consider this curve, the intersect points, this one, and this one, are fixed point. This one, and this one. Fixed point. Why we call these points fixed point? Because if you compute, take it. Yep. Now, if you consider this one, this point, it doesn't work. Okay? If you consider, for example, this point and call it P and f of P, because P is both on y equal to x and y equal to f of x, then P will be equal to f of P. We call such points with this property, we call it the fixed point. Okay, so here I have written the definition of the fixed point. If f of P is equal to P, then we say that P is a fixed point of function f of x. In fact, we want to use this property to finding the root of the equation. Okay, if we want to use something like this, we consider f of x equal to g of x minus x. Okay, now if x be a fixed point of g, okay, if x is a fixed point of g, then g of p equal to p. Look at here, g of p equal to p. So f of p will be g of p minus p, and this is equal to 0. And what does it mean? And this means f of p equal to 0, and this means p is root of f of x equal to 0. This is the idea and the clue of the fixed point method. So what can we do? In fact, we have to find a relation like x equal to g of x from f of x, and we find the fixed point of g. In this case, in fact, we have to we found the root of f of x. Look at here. For example, consider a function like f of x equal to x to the power of 3 minus x minus x plus 1. Okay, if we, for example, consider g of x equal to x equal to x3 plus 1 to power of 1 over 3. Okay, if we find the root of the fixed point of g of x, in fact we found the root of f of x. This is the clue. Now let me continue by the concept of the fixed point equation. For example, consider g of x equal to x squared minus 2. If we want to find the fixed point of g, we have to consider p equal to g of p. So we will have an equation like p squared minus p minus 2, and we write it to form p plus 1 times p minus 1, and if we consider this equal to 0, this get p equal to minus 1 and p equal to 2. So in fact we have two fixed points for this function. Let me show it on a figure. This is the graph of y equal to x to the power of 2 minus 2. Okay, and this is the line y equal to x. The intersect point is here and here. The first one is minus 1 and the second one is 2. So there is two fixed points, p equal to minus 1 and p equal to 2 as fixed point of g of x equal to x2 minus 2. Okay, this is the in fact the geometrical illustration of the fixed point for function g. Now it's very slow. My computer is very slow. I don't know why. Now, let me show you another example for the meaning of the fixed point. I suggest you take a calculator. I use my computer calculator. Okay, put it on radians. Okay, and press cosine function, cosine key on your calculator. The first one is cosine of 0, it will be 1, and then press the cosine again, it will be 0.540 and so on, you can see here, and press cosine again, it will be a new number, again, you look the number again, and more and more and more. If you do something like this and press cosine several times, you can see some digits after the decimal point from left to right will be fixed step by step. Okay, the first one 7 is fixed, then 3 is fixed, and then 9 will be fixed. Look, 9 will be fixed. And the other one 0 will be fixed, 0 after 9, look, 0 fixed, done. And the other one should be 8, after 0 should be 8, 8 fixed, after 8 should be 5, look, after 8, 4, 5, 4, 5, 5, and it's fixed. And the other one should be 1, 0, 1, 0, okay, and if you continue in this way, finally you will get p equal to 0.70390818513 and so on. This is exactly the process of the fixed point iteration. Okay, I can show you this on this graph. If you consider this is a part of the cosine function and we start from, for example, a number like 0.3, okay, and we push cosine on 0.3, we get a number very close to 1, like 0.921 and so on. Okay, and if we push again the cosine, we get this new number. Okay, and again, it will work. Again, look, you can see that it start to move and will go close to the intersection of the line, this line, y equal to x, and the graph of the cosine of the x. Okay, this is exactly the meaning of the fixed point iteration. But now let me finish this show. Now there is some question here. In fact, we want to know when do we have a fixed point, and if the fixed point is unique or it's not unique, or something like this. In fact, we have a theorem here. In this theorem, we have two parts. The first part says if f equal to c of a and b. And what does it mean? This means that f is continuous on the interval a and b. F is a continuous function on interval a and b. And in fact, the derivative of f is also continuous. Okay, exists and continuous. And then f has a fixed point on a fixed point p belong to a and b. So in fact, if the continuity of f, okay, means we have a fixed point for the equation. But if in addition f prime of x exists on an interval a and b, and the absolute value of f prime of x be less than k, and k will be less than 1 for all x in the interval a and b, then the fixed point is unique. The fixed point is unique. This is the most important theorem in the fixed point story. For the proof of this theorem, consider f will be equal to a, or f of b will be equal to b. So there is nothing to say, and in fact we have done, because the fixed point is a in this case, and fixed point will be b in this case. But if any of these two cases have not happened, in fact we will have f of a should be greater than a, and f of b should be less than b. Now we define a new function like h of x to form f of x minus x. Since both f of x and x are continuous, in the hypothesis we had f of x is continuous, and we know y equal to x is continuous. So h is the difference of two continuous functions, so h will be continuous. And h of a, if you compute h of a, it will be, look at here, h of a is f of a minus a, and here it will be positive by this equation. Okay, and if you consider h of b, it will be f of b minus b, and by this equation it will be minus. Okay, so h of a is positive, h of b is negative. So by the intermediate value theorem, there exists a point like p star in interval a and b, such that h of p star should be 0. Okay, so 0 should be equal to h of p star, and h of p star is f of p star minus p star. And what does it mean? This means f of p star equal to f of p star equal to p star. And what does it mean? And this means P star is fixed point for function f. And this complete the proof of the first part of the theorem. And what about the next one? For the next part, let f prime of x, the absolute value of f prime of x, be less or equal k, and it is less than 1. Okay? And by using of the proof of contradiction, we suppose that we have two fixed points, for example p star and q star. Also, we suppose p star is not equal to q star. In fact, p star is not equal q star. And we can assume that p star is less than q star, or q star less than p star. There is no difference, and there is no effect on the proof of the theorem. The mean valued theorem tells us there exists an R in the interval p star and q star such that f prime of r equal to f of p star minus f of q star divided by p star minus q star. Okay? Now, consider the difference between p star and q star, the absolute value of p star minus q star. It will be f of p star minus q star. Okay? This is true because we know f of p star equal to p star and f of q star equal to q star. In fact, we put instead of p star f of p star, and we put instead of q star f of q star. Using here, by this equality, we can get f of p star minus f of q star is equal to f prime of r times p star minus q star. We put the absolute value here, and instead of the absolute value of p star minus f of q star, we put this absolute value. But we know that f prime of x is less or equal k, okay, for all x in the interval. So here f prime of r is less or equal k. So we put instead of this k here, and we get k absolute value p star minus q star. But k is less than 1, strictly less than 1. So it should be less than absolute value p star minus q star. So in fact, we get absolute value of p star minus q star is less than absolute value p star minus q star. And this is the contradiction, because this cannot be less than this one. It should be less or equal. This is the contradiction. And in fact, the assumption p star is not equal q star is not true, and they should be same. And this continues the proof, this complete the proof of the theorem. As an example, consider the function g of x equal to x squared minus 1 over 3. Let me have a look at the theorem one more time. Here. Doesn't work. Look at here. For the first condition, we should have f of x belong to a and b. So let me go to the problem. Look at here. Consider g of x equal to x2 minus 1 over 3 on the interval minus 1 and 1. It's clear that every point g of x belong to minus 1 and 1 for all x belong to minus 1 and 1. It's clear that this is true. So now we consider the maximum value of the absolute value of g prime of x. Look at here, g of x is equal to x2 minus 1 over 3. So g prime of x should be 2x over 3, and the absolute value of g prime of x over the interval, it should be the absolute value of 2x over 3, and it should be less or equal 2 over 3, and this is less than 1. Yeah, and by the theorem, in fact, there exists a unique fixed point in the interval minus 1 and 1. Okay, now consider we want to find this fixed point. Okay, we want to find this fixed point. The function is x2 minus 1 over 3 g of x equal to x2 minus 1 over 3. Okay. Now, if p equal to g of p equal to p2 minus 1 over 3, then we get a second order equation and we can find p in this form. Okay, and now if you have a look at the figure of here, you can see here this curve is the x2 minus 1 over 3, and this is the line y equal to x. The intersection is here and here. This point is this point, and this one is this point. Both of these two functions are the fixed point, but the clue is that in the interval minus 1 and 1 there is just one fixed point, and the interval, for example, 2 and 4, also there is just one fixed point. But if we want, for example, talk about the interval minus 1 to 4, the theorem cannot work because there is not a fixed point, a unique fixed point in the interval minus 1 to 4, but in the interval minus 1 and 1, and the interval, for example, 1 and 4, there is just one fixed point and there is no problem and everything will be okay. Now, consider another example. Let g of x equal to 3 to power of minus x on the interval 0 and 1. Okay, if you compute g prime of x, it will be minus 3 to power of minus x ln 3, and this will be minus. Okay, this will be minus. Now consider g1, it will be 1 over 3 is less or equal g of x less or equal 1, and this is equal to g of 0 for all x between 0 and 1. So for all x belong to 0 and 1, we have g of x equal to 0 and 1, and this is good because the first condition of the fixed point theorem is this one. But if you compute g prime of 0, look at here, g prime of 0, it should be minus 3 to power of minus 0, it will be 1, okay, minus 1 times ln 3, and it will be minus 1.09, and the absolute value of this is this, and this is greater than 1. So the second condition of the fixed point theorem has not satisfied, and it says in fact it says maybe the unique fixed point is not exist. Okay, maybe we have more than one fixed point. But if you plot the graph of the function g of x equal to 3 to the power of minus x, you can see that there is just 1 point. So in fact the theorem, I want to say the theorem, maybe the condition of the theorem has not satisfied, but there is just one fixed point for the function. You have to note to this point. Now let me show you an example, and let me show you how we can compute the fixed point of the equation and use it for finding the root of an equation. Consider the equation x to the power of 3 plus 4x squared minus 10 equal to 0. By using the fixed point theorem, we can find out that there is a unique root in the interval 1 and 2. Okay, so we have to construct a g of x equal to x from this equation. For example, consider we keep 4x2 in the left hand side and put minus 10 and x3 in the right hand side. So we get 4x through x squared equal to 10 minus x3, and if we compute x, it will be 1 over 4 10 minus x3, and if we take square root, we can get x plus equal to plus minus 1/2 10 minus x3 to power of 1/2. Okay, also we can find several different forms of x equal to g of x. For example, we can put here in this equation, we can put x in the left hand side and write in the right hand side x minus x3 minus 4x squared plus 10. This is A. Or for another one, we can keep here, look at here, yeah, here you keep for this one, you keep x3, look at me, x3 equal to 10 minus 4x squared. Okay, now divide both sides by x, yeah, let me see, divide both sides by x, okay, to get x squared equal to 10 over x minus 4x, and take square root, x should be 10 over x minus 4x to power of 1/2, and this one we get this one. And for C we can use something like this, and D and E, we can have several different forms of g of x, but there is no guarantee that all of this function works correctly. For example, let P0 be 1.5. Okay, in this table you can look for A, I mean for this one. This is A. If we use the process of the fixed point, we can see that after 4 iterations, we goes in fact to infinity, and there is no convergence. Okay? And for example, for B, for here, for this one also, after 4 iteration, after 3 iteration, we get to the square root of a negative number, and this is not impossible also. But for C, D and E it will work. Look at the functions for C, D and E. For C, for example, this one, D this one, and E this one. the function will works. And in fact, after 30 iteration for C, we get the root of the equation, and in fact the fixed point of G. For D after 15 iteration, and for E after just 4 iteration, we can get the fixed point and the root of the equation. Now let me complete the theorem of the fixed point theorem, and in fact conclude consider a new condition for the convergence to the unique fixed point. We had the first two parts before. If f belong to C of A and B, and f of x belong to A and B for all x in A and B, then f has a fixed point. This is the existence of the fixed point. We have proved it. And in addition, if the absolute value of f prime of x less or equal k and less than 1 for all x in A and B, then the fixed point is unique. This is the uniqueness. But in this case, for any number p0 in the interval A and B, the sequence defined by Pn equal to f of Pn minus 1 converge to the unique fixed point P star for f, and the P star is in the interval A and B. Look at the proof. The proof is very easy. You have to just consider the absolute value of difference between Pn and P star. Pn is in fact members of the sequence, and P star is the fixed point. If we put instead of Pn fPn minus 1, this is Pn, and P star we put f of P star, and we use the mean value theorem. We can put f prime of r dot absolute value Pn minus 1 minus P star by mean value theorem. But in the hypothesis of the theorem, we had the absolute value of f prime of r is less than k. So we put instead k, and we get this one. Now, if k is less than 1, then the distance between two fixed points, in fact between Pn and Pn minus 1, is shrinking every iteration. In fact, the absolute value of Pn minus P star is should be less than Kn times P0 minus Pn. Why? Because here we can again use the mean value theorem. In fact, we can say that this is less or equal k f prime of r dot Pn minus 2 minus P star. Okay, and this one again less or equal k, and we get less or equal k squared Pn minus 2 minus P star. And if we continue in the same way, finally we get this is less or equal Kn times P0 minus P star. Okay, and this means that the absolute value of Pn minus P star is less or equal Kn, the maximum value between P0 minus A and B minus P0. So in fact, if we repeat and repeat and repeat, in fact this goes to 0, and it means Pn goes to P star. Okay, why this is true? Because here we told k is less than 0, so the limit of Kn when n goes to infinity, it should be 0, and finally we will get Pn minus P star, okay, less or equal 0, and this means Pn minus P star should be 0, and this means Pn converges to P, and this completes the proof. And we can see in fact, this is the previous example that I told you. The technique of the fixed point method is that we start with a number, for example, p equal to 1, okay, and we goes up until we receive to the graph of the function. Then we go to right until we intersect the y equal to x. Then go down until we intersect the graph, the curve of the function again, okay, like this. Then go to left until we intersect the y equal to x, and we continue in the same way. We continue until we arrive to the final in fact point. Now we have a very important corollary from the theorem. The corollary is this: if G satisfies the hypothesis of the fixed point theorem, okay, then bounds for the error involved in using Pn to approximate P are given by the absolute value Pn minus P less or equal Kn maximum between P0 minus A and B minus P0, and this Pn minus P is less or equal Kn over 1 over K, the absolute value of P1 minus P0 for all n greater than or equal 0. In the proof of the previous theorem, in fact in the fixed point theorem, we got the absolute value of Pn minus P is less or equal Kn absolute value P0 minus P, and this is less or equal Kn maximum value of P0 minus A and B minus P0. Now, for n greater than or equal 0, the procedure we use in the proof of the theorem, of the fixed point theorem, we get, if we consider the absolute value of difference Pn plus 1 minus Pn, and we put instead Pn plus 1 Gpn, and instead Pn Gpn minus 1. In fact, this is Pn plus 1, and this is Pn, okay, and we use this, we can get K Pn minus Pn minus 1, and if we continue in the same way, finally we get the absolute value of Pn plus 1 minus Pn is less or equal Kn absolute value of P1 minus P0, okay. Now let m be greater than n and greater or equal 1, and consider Pm minus Pn, okay. Because m is greater than n, we can add and subtract some terms from Pm minus 1 minus Pm minus 1 plus Pm plus 1. And we continue in the same way until we arrive to Pn plus 1 minus Pn plus 1. Now, by the triangle inequality, we can divide this absolute value to several different absolute value by two terms. So it should be less or equal the absolute value of Pm minus Pm minus 1, the other one Pm minus 1 minus Pm minus 2, and so on until we get the absolute value of Pn plus 1 minus Pn. In the previous slide, we get for each two Pn plus 1 and Pn, the difference between these two terms, we get this is less or equal Kn P1 minus P0. So we apply this inequality on each term here. For this one, it should be Km minus 1, absolute value of P1 minus P0. For this one, Km minus 2. And finally, Kn, the absolute value of P1 minus P0. Now, we factor kn absolute value p1 minus p. We can get 1 from here, k from the previous term, k2 until km minus n minus 1. So, we know that by the theorem, if m goes to infinity, pm goes to p. So the absolute value of p minus pn should be the limit of the absolute value pm minus pn m to infinity is it's less or equal kn, the absolute value p1 minus p0 sum from 0 to m minus n minus 1 k I, and it's less or equal k and absolute value p1 minus p0 sum from I from 0 to infinity k I. But this sequence is the geometric series, okay, with ratio k, and k is between 0 and 1. So it converge to what? To 1 over 1 minus k. So we can get, in fact, the final result in the right hand side, that p minus p1, the absolute value of p minus p1 is less or equal kn over 1 over k, 1 minus k times the absolute value of p1 minus p0. And this completes the proof. Thank you for watching this lecture. Please subscribe my channel in YouTube and follow the lecture until the end. In the next lecture, we study the Newton method, and also I want to solve some problem for you. Okay, thank you.